In Chapter 12, we look at liquids, solids, and the forces holding those together between molecules, the intermolecular forces. In the first section, we'll cover the first three parts: interactions between molecules, properties of liquids and solids, and intermolecular forces in action in the model of surface tension and viscosity. So, talking about the interactions between molecules, what are some examples of that? Well, one is the idea of flavor. How do we sense flavor? Well, that's caused by the interaction of molecules that are in something that we're consuming with molecule receptors that are found on the surface of our tongue. So, without those receptors carrying out an intermolecular reaction, we wouldn't have flavor or taste. Flavor also involves the reaction of these molecules in food or drink with receptors that occur in the nose, in the sinus area. So the figure that you see here shows a caffeine molecule, and this is one of the substances that we know is important to us in our coffee, our tea, our soft drinks for keeping us awake and jittery, but they also are responsible for some of the bitter flavors. So one of the reasons people that don't drink coffee don't like coffee is for this bitterness, and part of it comes from caffeine. There are other things, of course, that cause bitterness as well. So taste is originating from interactions between molecules. You have to have specialized cells on the tongue to do this. These receptors are going to only react with certain types of molecules. So they're very specific to those types of molecules. And when there's an interaction, that triggers a signal to your brain. And your brain interprets that as a flavor, such as in the case of caffeine, bitter. Now, the reason our systems are designed to react to bitter tastes in particular, and the reason we find them unpleasant, is because that many of the molecules that trigger those bitter receptors are also poisons. So things that we think of as poisonous tend to be bitter. And it's probably an evolutionary adaptation to help us avoid poison. So when we taste something bitter, our instinct is to spit it out, because evolutionary-wise, that is a disadvantage to consume that. That may poison an individual. Those specific interactions that we're looking at between the molecules that are in, say, the coffee that you drink that tastes bitter and those receptors on your tongue are caused by the attractive forces that exist between molecules, known as intermolecular forces. It's not a force strong enough to create an actual bond, but it is enough to hold those molecules together to a certain extent. Now, intermolecular forces are vital to us as living organisms because we depend on them for many of our physiological processes, the processes that keep our body running. Less specific intermolecular forces do exist between all molecules and atoms. There's a certain attraction between any two objects at all. But intermolecular forces tend to be a little bit stronger than just a random attraction between two particles. And they're responsible for the very existence of liquids and solids. So in Chapter 11, we looked at gases. Now we want to look at what is different about a liquid and a solid. Why are they such a different category from gases? Now, looking at any of those categories, liquid, gas, or solid, the state of a sample of matter is dependent upon the magnitude of those forces that we're talking about, those intermolecular forces, relative to the amount of thermal energy that there is in the sample. Okay? So thermal energy we're going to generally interpret as heat. That's not the only source, but how hot is the sample? What's the temperature of the sample? Okay? So molecules and atoms that compose matter are in constant motion. There's a random motion that increases the more we increase the temperature, the more thermal energy that we put into that system. Now, if we have very weak intermolecular forces, very weak bonds holding those molecules together relative to the amount of thermal energy, the more likely the sample is to become a gas. If you have stronger intermolecular forces relative to thermal energy, then you're going to be looking at either a liquid or a solid. Just sort of an example of that, if you think of intermolecular forces as people holding hands, gases are maybe like little kids on the playground that, don't really want to be holding the hand of the person next to them. Oh, they've got cooties or something. So they're not holding on very tight. And if you've ever played the game Red Rover, you know that you line up a bunch of children and they hold hands together and they call Red Rover, send some, so-and-so right over. And that person goes running and they try to break through the line while the kids that are holding hands in line try to hold their hands so tight that person can't break through. Well, where they can break through easily, that would be breaking that bond in between. That would be an example of, going into the gaseous state when you talk about molecules. Where the people are holding their hands tight enough that they can't break through, that's where you're looking at it holding itself together in more of a liquid or a solid. So, in contrast to gases, where we have molecules or atoms that are very far apart, relatively speaking, relative to the size of the particle, the molecules or atoms in liquids and solids are actually close to one another, and they're actually in contact with one another on a pretty much constant basis. Now, the difference between a solid and a liquid is simply the freedom of movement of the molecules in that solid or liquid. So in a liquid, atoms and molecules are in close contact and they are touching, but they're still free to kind of move around and slip and slide over each other. It's sort of like going to a crowded nightclub. So there's a lot of people there, but you can still manage to work your way between them and slip your way through and get across the room if you need to. In a solid, the atoms or molecules are fixed in position. Okay, now thermal energy still causes movement, but it causes them simply to vibrate around a fixed point. So this would be, sardines in a can. They're crammed in there. They're really not going anywhere. There might be a little room to wiggle, but other than that, they're really kind of staying in place. So just a visual example of that, the relative interaction of these particles and their distance one to another. So gas versus liquid versus solid. Solid, very rigid, fixed structure, has a fixed shape. Liquid, it's going to take on the shape of its container, but notice the molecules are close together. The gas just moves around in the space available to it. So, just a reminder about gases. Gases have low density when you compare them to liquids and solids. There's no definite shape. It assumes the shape of its container. There's not a definite volume, so you can easily compress a gas. And there are very weak intermolecular forces relative to the amount of thermal energy in a gas. Example, carbon dioxide gas, the air that we breathe, oxygen, nitrogen, these are all gases that we're familiar with. Now, properties of liquids. A liquid will have a high density compared to a gas. It does have an indefinite shape, so it assumes the shape of its container. It does not have a fixed rigid shape, but it does have a definite volume. So a liquid is not easy to compress. You can measure the volume of a liquid, whereas the volume of a gas is really dependent upon the container that you have it in. A liquid will have moderate intermolecular forces relative to thermal energy, certainly stronger intermolecular forces than those found in a gas, not quite as strong as those found in a solid. An example is water. So that's our classic liquid, the one that we see the most. Solids have high densities compared to gases. They have definite shapes and definite volumes. They're not easily compressed. They don't assume the shape of their container. You can measure them. They have strong intermolecular forces relative to the amount of thermal energy in them. An example of that would be, say, a sugar cube. Solids can be crystalline in an ordered shape. So for instance, if you've ever looked at tiny little crystals of table salt, you know that they form little cubes, or they can be an amorphous solid, just in a disordered mass. So if you have a piece of metal, for instance, that you're looking at, that piece of metal might be, you can hammer it flat, you can draw it into a wire, you can move it around, so it doesn't have an ordered structure. It sort of can be a little more flexible. So it's still going to maintain its shape and its volume once you put it into a particular shape, but you can change the shape more easily than you can in a crystalline solid. Now, just looking again quickly at shapes of liquids and solids, because the molecules in liquid, such as water, are free to move around each other, they flow, they assume the shape of their container. In a solid, now if we take that same water that was in a liquid form and we freeze it into place, the molecules become fixed in place and they form this orderly structure. So they can no longer slip over one another, they form this space. And notice in ice, one thing that's very unusual about ice as compared to other solids, usually when you go from a liquid to a solid, the molecules, instead of being able to slip over each other, sort of compact themselves tightly, and the volume actually decreases going from a liquid to a solid. They contract. In the case of ice, when they go into a solid state, notice they form this orderly structure where there are gaps in between. So they actually are further apart in the solid than they are in the liquid. And so ice expands. We're familiar with this idea. We have to be careful when freezing things in a container that it doesn't expand and crack the container. And it also makes the ice less dense than the liquid water, and so it floats on that. Okay, just be aware these molecules are vibrating around fixed points, even though they're held in shape. So intermolecular forces that we're talking about, just the forces that are holding the molecules together, and we will look at those in more detail toward the end of the chapter, what causes those. But for now, how do we know about intermolecular forces? How do we sense those or see those? Well, two of the ways we can see them are in terms of surface tension and viscosity. And those are both relative to liquids. Surface tension is the property that allows there to be almost a skin on top of water. So if you've ever had a glass of water and played with it and just touched your finger barely to the top, you know how the water sort of almost leaps up to grab your finger, and as you pull up, the water sort of comes up with it. That's an example of surface tension on water or on a liquid. Water in particular has strong surface tension. Paperclip, if you're very careful, you can actually float a paperclip on water. It's just being held up by surface tension. So if you, for instance, take another paper clip and unfold it to make a little scoop, put one on top of it, and then slowly lower it, you can usually get that paper clip to float on there. Now, you couldn't do the same thing on gasoline. The intermolecular forces in gasoline are weaker compared to those in water molecules. Water is a pretty special case, and in the very last section of this chapter, we'll take a closer look at it. But one of the amazing things about it is this idea of surface tension. Now, if I do something to break that surface tension, such as add a drop of soap, I won't be able to get this paperclip to stay on top anymore. It would sink. It's kind of a fun experiment to do if you've ever got some spare time. Try floating a paperclip and then get a drop of soap and just put a drop of soap in the water. You don't even need to drop it on the paperclip. Just put it in the water, let it kind of stir around, and eventually it will break up that surface tension in the water and that paperclip will sink. All right, so what is it about the water molecule and the intermolecular forces that are causing this idea of surface tension, that are causing this property? Well, if we look at a molecular view of the molecules that are in this water, if we are under the surface, below this very top layer, and this is a little misleading because they almost make it look like, you have these balls floating in water. Well, that line is actually right here. These are the molecules on the very top. This is the top surface of the water here. Below the surface, you're getting each molecule interacting with 6 of its neighbors. So it's seeing forces equally pretty much from all sides. Now this again is shown in 2 dimensions, but imagine it 3-dimensionally. Those molecules are surrounding it everywhere. Okay, and it can interact with up to, about 6 of its neighbors. Well, this one on the surface is only seeing a pull downward. Okay, so there's a net pull or dipole going down. This one doesn't have a net pull in any direction. It's being pulled equally from all sides. This one is seeing more force downward, and so it forms this sort of stronger connection going downward than upward. And it pulls everything downward to kind of form that skin that you see on the water. This can also be used to talk about why water forms droplets, why it forms these little spheres. Okay? So if we take water and we squeeze it out of a dropper, or if it falls off the end of a piece of grass or something, a drop of dew, we'll see that it forms a little sphere, and that's because of the surface tension being caused by the attractive forces between the water molecules. All those molecules that are on the surface are being drawn inward. They're seeing intermolecular forces pulling them in rather than outward, and so they draw up as tightly as they can, that shape being a sphere. Now, experiments were done on the space shuttle to look at this idea too. Is it gravity causing this? Well, no, there's no gravity there. So if you take water and you release it in this zero gravity, you'll see these floating spheres of water. They just draw in on themselves, and it's almost like this bubble floating around. All right, so that's one property. Another one is the idea of viscosity. And viscosity is simply the measure of a liquid's resistance to flowing. So we're used to certain viscous liquids. Water doesn't tend to be a heavily viscous liquid compared to some others. So for example, motor oil. So if you think about pouring motor oil out of a can, you know that it seems to be thicker and it pours more slowly than water or gasoline, so it's more viscous. Maple syrup, very thick. Honey, any of those type of things, those are more viscous than water. So viscosity is just resistance to flow. Viscosity will be greater in substances that have stronger intermolecular forces. It's simply because those stronger forces are keeping the molecules from moving around over each other freely in a liquid. They kind of hinder the flow. They slow things down. So when we have long molecules, such as those that you find in motor oil, they're very long hydrocarbon molecules. Sorry, didn't mean to cross that out. Those tend to form viscous liquids because what happens is those long molecules, those long arrangements of carbon atoms, when you get several of those together, what they do is they start to tangle themselves up. Okay? And you can imagine if you've got this big entanglement that it's going to be a lot harder for those to move around and move over each other as when you have, say, water molecules with these little fixed spheres that can interact with one another. So, maple syrup, more viscous than water, molecules are interacting more strongly, they can't flow past each other very easily. So those are some of the properties that we can see from intermolecular forces. In the next section, we'll look at some more properties that are caused by intermolecular forces, and those include evaporation, condensation, melting, freezing, and sublimation. So we're going to look at phase change in liquids and solids in respect to intermolecular forces.